we're going to talk a little bit about pedigrees. A pedigree basically is a family tree that tracks traits down the generations of a family. So each of these squares and circles represents individuals. And when you have a horizontal line connecting two individuals, it indicates that they are mating. And the offspring of that mating would be underneath those people. So you can see that these two people got married and they had these 4 children. Squares, him, represent males. Circles, her, represent girls. Now pedigrees are useful for many reasons. They're helpful to be able to track generations, diseases or different conditions in generations, but they're also helpful so we can figure out, based on what someone's offspring is or what their parents are, we can figure out what their genotypes or what their genetics are. So here's one example. This pedigree illustrates the blood type of a family over 4 generations. Notice that the 4 generations are indicated by Roman numerals. So this tracks blood type. So just a little bit about blood type and how it works. You probably should know this, but blood type is controlled by 3 different alleles, not 2. The A allele, the B allele, and the O allele. Now A is dominant to O, B is dominant to O, and A and B are co-dominant. Okay, so in other words, if someone has blood type A, they would have to have both A alleles or an A and an O allele, because you know that A is dominant to O. If someone had blood type B, they could be BB, 2 B alleles, or B and an O, because again B is dominant to O. For someone to have blood type O, they would have to have both O alleles, and that's because it's recessive. To have that trait, you'd have to have both recessive alleles. And then lastly, to have blood type AB, you guessed it, you would have to have the alleles A and B. Alright, so the question in this pedigree is, what is this person's blood type? And you're going to see problems like this. And to figure this out, we have to look at either its parents, and this person's parents are not there, or in this case, we would have to look at the offspring. So we look at the offspring, and the information from this offspring, just these 3 guys, should tell us what that person's blood type is. Now in general, people with recessive traits are the most helpful. So this guy has a recessive trait. And why is it helpful? It's because I know for sure 100% what its genotype is. This person has blood type O. O is recessive, so this person must have 2 O alleles. And I know for a fact that this person got one of each of these O alleles from each one of his parents. I know he got an O from his father, which tells me right away that this individual must have an A and an O. And I know that he got an O from this parent as well. So far I know one of this person's 2 alleles. Let's figure out the other one. Well, it's helpful now that I know that this parent has AO. Okay, so we take a look at this offspring. This person has blood type AB, so it has an A allele and a B allele. So I know that this B allele did not come from this parent. Because this parent has AO. This parent can only pass on the A or the O. There's no way that this parent passed on this B. So where did that B come from? It must have come from this parent. So that parent has blood type B, and its alleles are, its genotype is BO. Alright. Now pedigrees are also helpful because they help us to determine the way certain diseases are passed on from generation to generation. So some diseases are recessive diseases, right? So you have to have both recessive alleles to have the disease, right? So the normal allele would be dominant. Some diseases are dominant, which means the allele that causes the disease just happens to be the dominant allele. So if you have one of each, you would have that disease. And some diseases are sex-linked. That is, the gene for that disease is located on the X chromosome. And on a test, you might be given a pedigree and you might not be told what the mode of inheritance or how that disease is passed on, and you would have to figure it out. So here's how you do that. On any test or any kind of pedigree, if you're given it and you're not told, you would have to figure out 2 things. Is this disease sex-linked or not? And when it's not, we would call it autosomal. So determine if it's sex-linked or autosomal. Then I have to determine if it's dominant or recessive. Alright, so first thing we do is we find out if it's sex-linked or not. Now here's the key. sex-linked diseases are always significantly more common in males. So you count up the number of males that have the disease. You count up the number of females that have the disease, and if there's a significantly more males with the disease, it would be sex-linked. So if we look at this disease, we've got 1, 2, 3, 4, 5, 6 males, 0 females. So in that case, that's pretty obviously sex-linked. Way more males than females, so this would be a sex-linked disease. Now I have to determine if it's dominant or recessive. To do that, I am specifically looking for this situation. If I see two parents who don't have the disease, but they have a kid who does have the disease, if you see that, it must be recessive, because these people don't have it, but they must obviously have the allele, because their kid has it. If they have the allele, but they don't have the disease, it must be recessive. So that's what we look for. If we see this, it's recessive. If we don't see that, we can assume it's dominant. So, do we see it? Yep, right there, and right there. 3 situations where people do not have the disease, but their kid does. That makes it sex-linked recessive. Okay, and once I know that it's sex-linked recessive, I know I can now write my genotypes and potentially solve genetics problems. So for instance, let's take this person for example. Okay, it's sex-linked, so when I write my genotypes, I have to do it on the X and Y chromosome. This guy is a boy, so right away I write down XY. Okay, now I ask myself, does he have the disease? Yes, he does. The disease, remember, is only on the X chromosome, not on the Y chromosome. So this guy only has one allele for this gene, and because he has the disease, he must have the recessive one. We'll call that little a. It causes the disease. If we look at his brother is also a boy, so he's XY. His brother does not have the disease, so his one X chromosome must be normal. Okay, so males are easier. If we look at females, they're a little trickier. So let's look at her. Now, because she's a girl, we know she's XX. She does not have the disease, so I know she must have one normal allele. Question is, what's the other one? Do we know, is she big A or big A little a? Well, we have to look at her parents to figure that out. And if we look at her dad, we know that her dad had it, so it must be this. And we know if he has a girl, he must pass on the X chromosome. So we know that this girl must be a carrier. She must be big A, little a. Okay? So that's how we figure out genotypes. Now let's take a look at another pedigree. Okay? So let's first of all figure out if it's sex-linked or autosomal. Count the number of males with the disease and the number of females. We've got 1, 2, 3 males, 1, 2, 3, 4 females. More girls than boys have it, so there's no way it's sex-linked. Remember, sex-linked diseases are always way more common in males. So if it's not sex-linked, we know it's autosomal. Now we determine if it's dominant or recessive. Do we see this situation? Two people who don't have the disease, but they have a kid who does. And no, we don't see that in this pedigree. Because we don't see that, we know that this is autosomal dominant, which means it's the dominant allele that causes the disease. So all of these people that have the disease must have one dominant allele. Everyone who doesn't have the disease, well, they don't have that dominant allele, would have to be both recessive alleles. Okay, now for these people who have the disease, have the dominant alleles, we want to know if it's big A, or big A, little a. So to do that, we have to look at the offspring. Now think for a second. Well, let's take a look at this offspring. This offspring doesn't have the disease, so it doesn't have that dominant allele. It must be little a, little a. I know he got a little a from each parent, didn't he? So I know that this parent must have a little a as well. So in that way, we're able to figure out the genotype of that person. Let's look at one more pedigree. Okay? So again, first of all, find out if it's sex-linked or autosomal. Count the number of boys and girls. I got 1, 2, 3, 4 boys with it, 1, 2, 3 girls. So there's a 4-to-3 ratio. So that should tell me right away that it is not sex-linked. This is an autosomal disease. Yeah, there are more boys than girls, but it's not significantly different. If it was sex-linked, I would see a significant difference. 4-to-3 is pretty much the same. So that tells me it is autosomal. Now, is it recessive or dominant? Well, here I see two people without the disease having a kid who does have the disease. That tells me it is recessive. So now I can fill in genotypes. So people who have the disease, they must have both recessive alleles. So all of these colored in guys must be little a, little a. Okay, people who aren't colored in would have a dominant A, and we'd have to figure out what the other one is. Well, if we look at this offspring, we know this person is little a, had to get a little a from each parent, so each of these guys must be heterozygous.